Sentinel is a fault detection and location system, effectively a radar system that's constantly monitoring the performance of the overhead line. It's looking to detect the normal, traditional sort of low impedance type faults, as well as those which are basically those faults that cause high currents to flow. But one of the main aspects of Sentinel is that we're trying to also develop the technology to identify very dangerous situations where an overhead line conductor can come away from its support and actually pose a serious risk to the public. Traditional faults on the overhead line are detected, or faults on the overhead line are detected using traditional protection systems. And following a fault, engineers are sent out to identify the location. This in itself can be costly, time consuming, and most importantly can also be dangerous to staff and to the public. This obviously has an impact on customer minute lost and also poor customer performance. Sentinel aims to be able to locate a fault within a couple of 100 metres of the actual location. This therefore will reduce time to identify the fault, enable us to get crews to the right location quicker and repair the fault and get customers back on supply much earlier. So being able to locate the fault, get there quicker, means obviously customers are off supply for shorter periods of time, which also reduces the customer minute lost figure and improves that. Now, in terms of a loss of life, you can't put a value on a loss of life, and hopefully this technology will show that we can do that. The technologies deployed within Sentinel include impedance-based and voltage gradient technologies, as well as signal injection using TDR. This is the technology that will detect the low clearance lines. Effectively, it's a digital pulse that is constantly sent down the overhead line, and depending on the reflection of that signal, a change will be seen. So on a normal line, if you like, it has a fingerprint. So this pulse will continue every couple of seconds down the line and come back, and that reflection basically overlaps itself if it's healthy. So every reflection will come back on that line and should remain the same. Where there is a change, which is a discontinuity within the line, will be seen by a change from its normal, shall we say, and from that point we can measure where that is on the line. It's all pole-mounted equipment. Basically, you have a control box, no different to, looks like a GVR type control box, and then above, connected to the overhead line, is a voltage divider and a current sensor. Normally, depending on the type of fault, obviously, if it's a fault that's caused protection relay to operate and hence trip a device, then you know it's beyond that point. We also basically no supply. So those type of faults that cause protection and devices to operate, we know within a certain area where that fault may lie. And yes, it's still time consuming. Depends on the terrain of where these are, because overhead lines go through forests, valleys, cross water. So usually the terrain, or in a lot of instances, the terrain can be quite dangerous and difficult. So there's also those faults that we call transient faults which don't cause protection devices to operate, and basically we rely on customers to phone in and say they're off supply, and from this, depending where those customers are, we can identify that a non-telemetry device may have operated on the network, say fuses, because we don't know whether fuses operate within the HV control room. Then in terms of the dangerous situation I was talking to before about the low line, at the moment in time, the only way we can identify those is by the public calling in and saying that they've seen something. In those instances, what we would do is we would dispatch an engineer immediately, and we would also identify off the HV network, as well as using geographical tools to identify that HV circuit, and we will actually make that dead to ensure safety of the public. Apart from actually being able to reduce customer minute lost in terms of your high current low impedance type faults, it's better customer service. You're removing danger from staff going out to identify and locate these faults. But what the most important thing is the safety. Basically, this system could prevent the loss of life where where a low line scenario occurs. This is one of the most dangerous situations that can be posed. So as well as looking at the actual development of the sensors themselves, we also had to look at where to deploy them. So we came up with we had to work on a criteria to understand the best locations for the devices. Following this assessment, we decided to actually put as many devices on the trial circuits as we could to ensure that we captured all the data we needed, and from there in the future to look at the optimization, how many sensors, and this was also dependent on the success of the technology itself and how far they could actually see down the overhead line. We identified 12 circuits actually. With these circuits were selected on fault history, because with it being a fault detection system, you want to actually have faults to actually prove the concept or prove the technology. And on those 12 circuits, we're looking to deploy a total of 150 units. To date, we've installed 110 units so far. We've got some down in the Peak area, down in Lancashire, and in Cumbria. So right across, trying to get that total, that diverse sort of topology across all circuits. Prior to installation, we also had to go through a number of trial installs at the Academy, as well as producing operational documentation and to provide training, not only for the linesmen, but also for the control rooms, so that the control engineers understood exactly what we were doing during outages when deploying and installing this technology, as it's new to, as it's completely new and never been trialled before. Unfortunately, after a period of time, we find problems were identified with voltage drift problems with a large number of the Sentinel devices. What we've identified is that the voltages have been drifting up or down. Basically, we found that due to the environments in which these devices are installed, that we've had to deploy additional environmental protection within cable connections and additional earthing kits as well. So with these solutions in place, we have now been back to upgrade a total of 30 units, and we are happy to say that these solutions have actually worked successfully, and we're now into a period of deployment of actually upgrading the remaining of the initial installed 110 units. All devices then should start triggering on whenever there's a fault on the network, or should there be a change in characteristic like the lowered line scenario from its fingerprint. So all this development has been undertaken by Kelvotech at this moment in time, and developing those algorithms is a very, very difficult it's very, very difficult, and they're working round the clock constantly to refine these algorithms. Unfortunately, refinement only comes from tests and results, so the more faults we have, the more data they have, the better the algorithms will become. And this is sort of thing that will go on forever. As we do get more and more faults, even in time, even if it does get deployed as mass deployment across the whole network, then they'll be for always refining the triggers and the algorithms on these. So in November 2019, we carried out HV faults on the overhead line. These included face-to-phase and face-to-earth tests. These faults were most successful, and the software was able to detect to an accurate location within 100 metres of the actual fault that was applied. Earlier this year, we carried out a low line test where we lowered, again in controlled manner, the HV conductor of one phase to 1 metre and 2.5 metres above ground. Once the line was re-energised, the data was collated from all the devices within that trial circuit. What's come out of those results is that the algorithms at this stage were not sensitive enough to identify the change in electrical characteristics as the line was lowered, and as such, Kelvotech are now going through a refinement of those algorithms. We'll also be carrying out further controlled testing ourselves by applying faults to the network to accelerate that learning, shall we say, to ensure that we have sufficient data to prove the concept by the end of the project. Without that, it won't be able to go forward as a project, so we need to have that confidence that it works. With things being controlled, we can choose areas of the network where we don't actually have to knock customers off, or very few customers off. To improve that and to help us, we've actually developed a test platform which will be on the back of a low loader that we will be able to drive around to overhead lines and position in, well, depending on access, such that we don't, so actually we have less of an impact on customers. Just been built as we speak now. It's been designed, approved, and hopefully we will be taking that round to a number of locations to apply further faults. So where are we today then? So at this moment in time, we're in the process of carrying out an upgrade program to resolve the voltage drift issues that we've faced. We've got another 32 installations to carry out. A dashboard has been created, a live dashboard, which is basically a fault tracker, has been developed by Kelvatech as well. This is a web-based system which identifies all the trial circuits, all devices on those circuits, and will identify problems associated with each of the devices. So hopefully we plan to complete the upgrades and installations by at the latest February 2021. With the project being extended to 2022, this gives us in excess of a year to hopefully have sufficient number of faults to prove the technology, and also enable us to continue to refine the algorithms. As faults occur in the network, and we are advised by Kelvatech, we will feed back to Kelvatech what we find on site. This is a process which will help us to define the algorithms further to hopefully reach the target of faults within 50 metres or so. It wasn't part of the project at this moment in time to have real-time reporting. It's basically proving the concept at this stage. However, there is another phase of the project which is implementation of Sentinel into the network management system, which will be close to real time. This is all based on the development of the algorithms and the triggers to operate in a very short period of time. So what we're doing in the interim is applying a soft approach whereby Kelvatech will develop the algorithms, and it'll be a reporting system. They will, from Belfast, they'll phone in or email into the control room with details. We're looking at the functional specification for that at the moment, so we anticipate them to be able to contact the control room within 5 to 10 minutes of a fault. So if you take a low line, for instance, at the moment, could be there for days, weeks. We don't know, because we're always relying on the customer or on the public to come and advise us. So in terms of this system, whether it was 24 hours or 12 hours, in terms of developing those algorithms, that would still be a huge saving in time, but we expect that to be within the minutes. But once we've proven the technology, we will then go into a further development period where we'll look at changes we can do to this existing system. This trial is just basically proving the concept of the Sentinel. It does what it says on the tin, if you like, and if we are successful, we will move to that BAU solution.